We're going to start with lecture 4. This is a calculus of variations, part 1. And we'll be using, we're going to chapter 4 of the book, Introduction to Calculus of Variations. So what is calculus of variations? And you may not even heard this term before, but I will describe it today, and I'm hoping that we can get a good understanding of that. Calculus of variations is extremely crucial in the development of finite elements. In fact, you can take any governing equation and use calculus of variations to determine what is the approximate solution to the problem. That's how calculus of variations is going to give us the basis for this course. And so it's extremely important that you spend 8 hours. You spend a lot of time trying to understand this material. And calculus of variations can be used to solve many different problems. For example, if I were to take a chain and here, let me fix that now. Obviously, this is the hanging chain, and obviously this is the soap film bowl. So I apologize for that. So the examples where calculus of variations can be used, for example, you have the hanging chain. What if I want to know the shape of how that chain hangs when it's fixed at 2 points? What if if I have a soap film bubble and I take 2 rings that have soap and pull them apart? What is that shape? What does that shape take? If I have the path of light and that path of light is refracted through this material, what is the path that light is going to take? What if I have this globe and I want to know the curve that describes the minimum distance between 2 points, and I want to know what that curve is? And you may say, well, what does this have to do with this course? It has a lot to do with this course, because say I have an airplane and the airplane is flying and there's loads applied to the airplane. Well, that airplane is going to deform, and I want to know how that airplane deforms. So that's how calculus of variations can be used, is to solve these problems. And it can help you gain a fundamental understanding of many different problems, heat transfer, heart modeling, aircraft flying through space. We can solve a lot of different problems. So let's start with this simple problem that is called the geodesic problem. And I want to find the shape of the, I want to know this curve, what does this curve look like? And I want to find the equation y that joins these 2 points, x1, y1, x2, y2. And I want to minimize the arc length on this surface. That's the question that's being asked. And you all probably know the answer. You take a sphere and you draw a line, and it's a straight line, and that is going to be basically the minimum arc length. But what if I did not know? What if there was an alien that came to Earth and wanted to know how we solve these problems? And you may say, well, why are you trying to use mathematics in this class? Well, I have to, because you have to understand the principles of calculus of variations. There's no other way around it. So say I want to know what is the arc length distance. You can find what that is by taking a differential line element, and I'll be doing that a little bit later. And the length of a differential line element will be dx squared plus dy squared. And dy can be written as dy dx, and that's equal to y prime dx. So I can now go in here and expand it. And when I expand it, I'll get that dx is the square root of 1 plus y prime squared dx. And so the total length of this arch is the integral of this differential line element in here, and I'll be doing that later. And that becomes the integral of 1 minus 1 y prime squared dx. Now, what I want you to notice is something very interesting and something very exciting. As you can see here, y is a function of x, correct? Is y a function of x? And so, did you notice that this length L depends on the y? Do you see that happening? Do you see that happening?
Yeah.
Yeah.
Yep.
So if y was some crazy curve, the curve was going up and down all around the globe and come back to this point, is that curve longer than a straight line projected on this surface sphere? That line is way longer. So what's going to happen to L? It's going to be a bigger number. L is called a functional. It's called a functional because L depends on a function. Y is called a function because Y depends on a scalar quantity. I'll try again. If I plug in here a sine curve, so the curve goes up and comes up, that clearly is a longer curve, and so this L will be larger. So what is the one curve Y? What is the one curve Y that minimizes L? We know what that curve looks like because we know the answer. But what if we didn't know what the answer was? How do we find that? How do we find that curve? That's what calculus variations is about. Let's take this path of light example, and this is basically Fermat's principle. Say you have a refractive index of light in an inhomogeneous medium, and you have this equation here that says V equals C over N. V is the velocity in the medium, N is a refractive index, and C is the speed of light in vacuum. The Fermat's principle states that the path must minimize the time of travel, meaning the time of travel is definitely t equals the integral of dt. Well, dt is ds over v because that's what time is in relationship of the distance divided by velocity. That should give you clearly time. And I know what v is. V is c over n. So when I plug it in, I get this expression. Well, guess what? What I want to know now, I can write ds similarly to what I did here. Ds is this square root 1 plus y prime squared dx, and I can now determine what is t, and t is n x comma y times 1 plus y prime squared ex d squared. And so the path that must minimize the time of travel is basically what? I don't know. I had to find y that minimizes t. I had to find that. And that's not, it's not something you look at and you know what the answer is. It's not obvious, right? Another very interesting problem that's in my book, and I invite you to look at, is called the Brachistochrone problem. And the question being asked here is find the shape of a wire that joins two given points such that a bead will slide down due to gravity, and it will result in finding the path that takes the shortest amount of time. So clearly V is denoted as this, ds dt. You've seen this in physics. I know what ds is. Again, the same thing, 1 plus y prime squared dx. And I want to see what is the minimum minimum duration that will take for this bead to slide down. And that's found by this equation. And so what is the shape of wire? What is that wire shape that will minimize that time? And you'll be surprised what the answer for that is. It's not a sine, it's not a sinh, it's not cosine, it's not a straight line. But hey, guess what? What if I leave it to you as a surprising answer? And maybe you can do that. What if I now take the soap film bubble problem? And the question here is, what is the surface area volume ratio that's when it's minimized gives you a particular shape? That has to be, is going to be, any guesses? Anybody knows what this curve is defined by? If I separate these two guys, which is full of film, soap, and I pull it apart, you're going to create a soap film bubble. If you separate them more and more and more, this may detach and become a real bubble. Any ideas what this shape is? Very interesting question. It's going to be a hyperbolic function, okay? And you may say, well, how do you know that? Well, because we can solve it. We can find that. We can determine what is the minimum tension, because there's a tension here, surface tension basically, and when that surface tension breaks, this bubble comes apart. And so we can determine what is the minimum surface tension that causes a particular shape. We can also have the problem of an energy of a vibrating string. If I want to know the shape that vibrating string will take, all I have to take the kinetic energy minus the potential energy and minimize that. U is what I'm looking for. I'm looking for that shape of the string U that minimizes A. Guess what? The solution to this problem is the wave equation. That is a wave equation. And when you solve this, guess what? You get the answer that minimizes A. And so that's incredible. I can use calculus variations to find a function that minimizes a functional. Here, A is the functional. Here, A is the functional. Given a function U, what function U minimizes A? That's a very powerful idea. And I can use calculus variations to figure that out. So I'll cover this again because we wanna make sure that those that that you're able to study this. But I'll summarize it very quickly that what we're trying to do is to find U in this example that minimizes A. But U is a function of X and T. In a more classical calculus problem, you're given a function F, and if you want to find when the minimum maximum occurs, you have to find the derivative of F respect to X and set that equal to 0. In this example, that's 3x squared minus 6x. I can solve for X and I get X is 0 and X is 2. And if I want to know whether it's a minimum or maximum, I can examine the second derivative of F and then evaluate X equals 0 and evaluate X equals 2. And that's going to tell me, the sign of that is going to tell me whether it's a minimum or maximum. Well, that's how you do it with a single function that depends on X. But I can't do that with a functional A. I cannot just set the derivative of A respect to U and set that equal to 0 because A now depends on a function U, which I do not know what it is, and U depends on X and T. So you can see here that I cannot just simply take the derivative of A respect to U and do the same thing I did here. Very different problem. But I'm going to get and do something very interesting, and I plan to now teach by writing down in a minute. But say that you know what the real solution to the problem is. You know that y of x is the actual function that minimizes that functional. So say that I know what that is. I know what this y is that minimizes this time travel, this amount of time t. And so say that I know what that shape is. Assume for a second. What you want to do is construct another function y that's imaginary, it's virtual. It's not the real solution to the problem, is something else. And what I want to do is talk about that. I want you to notice how there's a distance between y and y tilde. And that's a fake, is a virtual distance. This distance here to this distance here, from the real solution of y, I know what y was, I know what y minimizes the functional, and this is the fake one y tilde virtual function y. And what I want to do, I want to say, okay, I don't know what the real solution is for real, but maybe this is the one and maybe this is the virtual function. This distance here is going to be chosen to be small. And this distance here, I'm going to call del y. And this del is going to be used for the rest of this course. And this del is going to look very strange in your mind because you've never seen anything like this, unless you've taken a course in calculus variations. And that's okay. That's okay if you have taken it. And if you have not taken it, get used to the idea of what this means. Del y is the difference between the real solution and the virtual function y. And you will notice how this del y vanishes to 0 at these endpoints. These endpoints very likely you know what y is. For example, let me give you an example. I have this hanging chain. This hanging chain is selected at 2 points. I know what y is at this point. I know what y is at this point. I don't know the shape of this curve. So, say for a second, I knew the shape of this curve. So that's what this point is, and that's what this point is. But I don't know what really that function is. I don't really know what it is. I have to find it. So y tilde x is a fake function, it's a virtual function, and this distance here between y tilde and y, I'm calling del y. I'm calling that del y. And del y will be equal to epsilon times eta x. Eta x is a function that's continuous. It's a continuous function. And epsilon is an infinitesimally small function, a scalar quantity. And I want you to notice when I set epsilon equal to 0, what happens to y tilde? What happens when I set epsilon equal to 0?
Y tilde is y.
So this function that's fake and virtual becomes a real function. Is that true? Is that true?
Yes.
Very good. This value here is going to be infinitesimal. Epsilon is infinitesimal. Del y is a virtual change, not a differential change. And del y is a change in y. Notice how at a given value of x, this del y is a change in y from the real solution to the virtual function, and that del y can also vary across x, right? The del y here is smaller. What happens when I get to these endpoints? What happens to del y?
Becomes 0.
Yes, it becomes 0. So notice how at the location where I specify the boundary conditions, notice how it vanishes. This del y vanishes. That's going to become very important when I cover subsequent theories. Okay? And so going back, what I'm trying to do, I'm trying to consider family of functions y tilde. The real solution is y. If I set epsilon equal to 0, my fake solution, my virtual function, becomes y. You can see that. So if I consider small functions surrounding y, the real solution, I can then study what's going on. And I notice very quickly how eta must be equal to 0 at these endpoints. You can see that. Eta must be 0 at these endpoints because y tilde is coincident with y. Do you see that happening?
Yes.
Now, I don't want you to confuse something that can be quite confusing. Del y is a change in y at a fixed value of x. But dy is not the same thing as del y. You've heard of dy before. Dy is a change in y due to a change in x. That is the tangent of this curve, right? But del y is not. Del y is a change in height from the real solution to the virtual function. And when eta is 0, this y tilde function collapses to y, which is a real solution. Okay, so with that said, I'm going to now, one more time, what we're trying to accomplish is to find the function y that minimizes the functional, and as a consequence, I'm going to consider a family of functions y tilde, they're in the neighborhood of y, and I'm going to examine that carefully. And this height, this difference height, I'm going to call the change in y, del y, or a variation of y. So that's what I'm calling that there. And so now what I want to do, I want to proceed now with going through the derivations, and I hope that this goes well and that you're able to follow along. So given a function f, what I want to do is, there's a max, there's a min. And I want to basically find where that maximum mean occurs for that function f. And that can be simply found as dfx dx equals 0. That's all you have to do to find that. And so that will be the derivative of f prime respect to x equals, sorry, that's incorrect. No prime. Set that equal to 0, and then you can find that. And if you f double prime is at that location x where this becomes 0, f double prime is greater than 0, then you have what? A local what?
Maximum.
No, it's a local minimum.
Minimum.
It's a trick question. If
You got
f
me.
double prime is less than 0, then I have a local maximum. It doesn't guarantee a global maximum, global minimum. And if I have the scenario where f double prime is 0, I have to start looking at maybe higher order terms. If I have several variables, and I had Hij is called the Hessian of a system, so Hessian of the system, and f was a function of multiple variables, x1, x2, etc. Then I have to then take the derivative of this. So I have to do Hessian, and so I get hold on. Okay, f xi xj. I have to examine this quantity here to determine whether it's a minimum or maximum. But the gradient of f equals 0 is what's going to give you the values of x1, x2, etc. that will basically cause this function f to be a minimum or a maximum, and the Hessian is going to tell you about the condition of that minimum or maximum. So this is a very different problem from what we plan to solve, and I'm going to step right into it. So give me a minute. So let's now start with functionals. So that's the topic for today, functionals. And what is a functional, right? What is a functional? It's a function of a function, okay, that takes a particular value which depends on the entire path of one or more functions, okay, rather than a number of discrete variables. So hopefully that's very clear. And I will be demonstrating that in a minute. So in calculus of variation, I'm going to have a function I. And this function of I is going to be equal to the integral from x1 to x2. And this function f here, and I do want to back up a little bit to make sure we all understand the convention here. So you're going to use a bracket for functional. So this bracket here is functional, and y depends on x, and y depends on x, and it's written in this manner. So you know clearly, this helps you understand clearly what is a function of what. So here, clearly I is a function of y, and y here is a function of x. So that's how you write this. And I here is called a functional. This is the functional here. Okay, that's your functional. And x here becomes the scalar quantity, right? And this is equal to x1 to x2 and f dx, okay? And f, what I'm trying to do is I'm trying to find y of x that minimizes I. That's what I'm trying to do. And it's not as simple as it looks like. You know, it may look simple to you, but it's not. Initially, you know, there's a lot of thought that needs to go into it. Okay. So let's now look at this more carefully. Okay. So this functional f, this f here, could depend on y. It could depend on y. It could depend on y prime, for example. And again, function of x, and then x, right? Dx. So it can depend on y and y prime, for example. And so here, I'm going to say that y of x is admissible. I'm going to say that. And in this case, I'm going to also say y of x is continuous and sufficiently differentiable so I can take the derivative of y, for example, right? And I'm going to say that this y of x satisfies the boundaries of this curve. Okay. Right. So that's what I mean with admissible, that this function y must satisfy these boundary conditions that I'm providing. So what I want to do, one of my favorite problems to really go and study this more carefully is called the curve of minimum length. I mean, that is the best problem to study this. Because in this problem, we know what the answer is, a straight line. So given this function, x1 and x2, x and y, and I have 2 points are specified. Anybody knows the curve that minimizes its length? What is that?
Straight line.
Straight line. So let's just draw a straight line. Close to straight line, but not quite. I tried. And now what I'm going to draw is another curve that's not the real solution. And I'm going to call this here y of x, and this one here y tilde of x. Okay, that's what I'm going to do. And I want to know what this distance is between here and here. So what is that distance? So I can take a differential line element, ds, and ds becomes, by a Pythagoras term, dx squared plus dy squared. And I can factor out dx, so I get 1 plus dy dx squared. Okay, so that's ds squared. And so the length then has to be the integral from x1 to x2. And I have what? The square root of this ds squared. So I have to take the square root of that. So then I have the square root of 1 plus 1 y prime squared d squared dx. That's exactly what I need there. And that is a function L. L now is my functional because it depends on y, x, okay, and y depends on x. And so very clearly, if I chose the red curve, can somebody confirm with me? If I chose the red curve as a curve Do you agree that L will be greater than if I chose a straight line? Do you agree with me on that?
Yeah. Yes.
I think it's obvious that that's the case. And so what I want you to pay attention, and I'm going extremely slow because it's not an easy idea to keep in mind, and I'm going to not complicate further everything. So let's go now and examine how to approach this problem. I'm going to consider the variation of a function, and that's what I'm after. So suppose we know the external function y of x, meaning that I know y of x. I know it's a straight line. That's what I'm saying with that. That makes I of yx a minimum or a maximum. It doesn't have to be a minimum. It could be a maximum. And I'll show you later how to determine whether it's a minimum or maximum. So we will consider then a family, okay, a family of functions in the neighborhood of yx. So I know what yx is. Yx is the one that minimizes or maximizes I, the functional I. Remember, functional I by a single parameter family. So I'm going to now consider y tilde of x equals y of x plus epsilon eta x. So that is what I'm going to consider now. And y tilde is going to pass through the endpoints. So this will pass through the endpoints. And so let me draw it one more time, what we're talking about here. And I'll draw it here. This is x, this is y. And I have this point. I know the solution to the problem is a straight line. Okay, I know what that is. So I know this is y tilde, y, and I know this is y tilde. Okay, and so these are the endpoints. And y tilde at x1 has to be equal to y at x1 because they're coincident. Y tilde at x2 equals y at x2. And clearly here, that must mean that eta at x1 is 0 and eta at x2 is 0. So I hope that's very clear that we're making y tilde and y collapse. So I can only vary y, I can only consider functions y in the neighborhood of y, but at the endpoints, they must be the same, they must be equal. Okay, and I'm going to now consider this epsilon right here. I'm going to consider this epsilon right here to be an infinitesimal scalar quantity. Okay, so epsilon is an infinitesimal scalar quantity. And eta x, I'm going to consider eta x to be an arbitrary function. That, and I want to make that clear that I want this eta x to be smooth, sufficiently smooth, meaning that you can differentiate it enough to be able to calculate this functional. And I also want to make sure, right, now that I defined how I want eta to behave, I also want to make sure that it meets these conditions here, because obviously at these points, clearly eta has to be equal to 0, because if this is 0, then y becomes y at this endpoint. So that has to be the case, and I hope that's clear. I also want you to notice that if I take the difference in height, that difference in height is this distance right here. This distance right there. And that distance is basically, I put this in the other side of the equation, I get eta, epsilon eta x, which I'm defining as del y of x. And so that's this height right here. That height right there is del y x. And I'm going to consider del y to be an infinitesimal virtual change in y, okay, at a fixed x. So I hope that's clear. I hope it's clear to you that this del y here, that is this distance right there, that del, and that distance del y, and let me make sure you understand it. That's del y. That height is a virtual change. Why is it virtual change? Because y tilde is a virtual function. Y is a real solution. So the distance between y tilde and y, which is y tilde minus y, that must be del y. And that's how we're defining this right there. So let me make sure that we all follow it. Are there any questions at this point in time?
Sir, is epsilon a constant quantity?
Epsilon is a scalar. Epsilon is an infinitesimal scalar quantity.
So it won't depend on either x or y, right?
Epsilon is not, it does not depend on eta. Epsilon is independent of eta. But it's a scalar quantity. So can you notice also that when I set epsilon equal to 0, y tilde also collapses to y. Can you see that happen?
Yeah.
Very good. So now let's do something very interesting. Okay. Let's now figure out how we can find the minimum, how to find y that minimizes I. That's really what I'm after. And it's perhaps not very clear how we will do that. However, what I'm going to do is something very interesting. What I'm going to do is I'm going to substitute anywhere where I have y, everywhere I have y, I'm going to plug it in for y tilde. And I'm going to change the problem altogether. So my I tilde, my I of yx of x, I'm going to now evaluate this function, but in the neighborhood of y. So I'm going to change this function so that it's I, but instead of y now, I'm going to select the family of functions of y, epsilon eta of x, and I'm going to look at what happens near there. Now, you agree now that this function I is no longer this function I, they're different. And so they're quite different. And so now this is y tilde really. So what I've really done for y, I have plugged in y tilde. That's really what I've done. I'm basically now evaluating this function I tilde. I'm evaluating this function I by plugging in y tilde instead. Instead of plugging the real solution y, I'm plugging in y tilde instead. And so that changes the problem. And so to give you perspective on what we've done, let me take you back here. Clearly, say for this problem here, I selected some other curve. That is my y tilde. If I plug in y tilde into here, now L changes. It's now no longer L, it's something else, right? So that's really what I've done. To make it clear, that's exactly what I've done now. So I've just plugged in a different function y into this functional I. And so I will have, therefore, a different functional I, which I'm calling I tilde. Okay. So hopefully that's clear. And what I'm going to do now, I want you to notice how I tilde has become a function of epsilon. I tilde has become a function of epsilon. And I can now basically study what is going on near epsilon equals 0. Because when epsilon equals 0, y tilde collapses to y. Those functions, y tilde collapses to y when epsilon equals 0. So it makes total sense for me to examine what is going on near, near epsilon equals 0. What is going on there? And I have good news for you. There's a way we can do this. So now that I tilde is a function of epsilon, I can now examine what is going on near epsilon. And I can use the idea of Taylor series expansion. Use Taylor series expansion to study that. And guess what? I know how to do that. I tilde of x near epsilon of 0 is I tilde. And guess what? If value epsilon equals 0, okay, plus the derivative of I tilde respect to epsilon at epsilon equals 0 times epsilon plus the second derivative of I respect to epsilon, and I tilde in this case, at epsilon equals 0, epsilon squared divided by 2 plus etc. And I'm sure you've seen how to do Taylor series expansion. What I want you to notice right now is that if I set I tilde, if I set epsilon 0 in I tilde, what do I get? What do I get when I set epsilon equals 0 on I tilde? What happens? What happens when I set epsilon equal to 0 here?
We get back the original functional.
We get the original function. And y is a real solution that minimizes I. So I get the minimum functional I. So I'm able to find the function y. So epsilon equals 0 here means I got I. I got I back. That's what I did. And I'm going to call this I1. I'm going to call this I2. Sorry, guys, I'm having some trouble. This is I1, and that's I2. I'm going to call this whole thing del I, and I'll call this whole thing del second variation of I. You're going to see that later. But I'm going to call this I and this first variation of I and this second variation of I. So hopefully that's very clear so far. I'm going to give you 3 seconds to kind of absorb this page after I say the following, because I am taking my time, and I have to take my time because this idea is highly complex. And we want to make sure that the fundamentals of this become very clear. Because if they're not clear, we're going to have trouble as we move along. And I just hope that we're gaining a fundamental understanding of calculus variations as I move forward. What I'm really trying to do, I'll repeat one more time, I'm trying to find the function y that minimizes I. That's what I'm trying to do. But to do that, I'm going to look at the family of functions here, y tilde, that's parameterized by epsilon and eta. and they have to satisfy these endpoints. And so eta at x1 and x2 has to be equal to 0. I'm also going to examine family of functions epsilon. They're infinitesimally small. I'm going to select functions eta. They're arbitrary. And what I'll notice here then is that y tilde minus y is epsilon eta. And epsilon eta, I'm calling the first variation of y. And what I want to do is then plug in the virtual function y instead of y. I'll plug it in here and then use Taylor series expansion on that around epsilon equal to 0, because I told you epsilon is an infinitesimally small quantity. So I hope that's clear. The second thing I want you to notice is that I want this. I want to find the function of y such that I tilde is equal to I. And if you notice here, I tilde minus I, so I can bring I to the other side of the equation. I tilde minus I has to somehow, you know, this here is going to dominate the Taylor series expansion. This right here. This term right here dominates the Taylor series expansion. So if I want I tilde to be close to I or equal to I need this del I to be 0 for this to be true. And so that's what I'm going to do next. I'm going to start now trying to then go from there. That's my goal, is to set this del I equal to 0, and then figure out how I can find the function y that makes it the minimum. That is my goal. So hopefully you have this written down, and I can continue going through this derivation. And I really need patience from your end, because these ideas require some thinking. So del I has to be equal to 0 for me to find the function y that minimizes a function of I. And so we just covered that this is di tilde, which is really y plus epsilon eta x, the epsilon at epsilon equals 0 times epsilon. I want to set this equal to 0. That's really what I want to do. And that's looking at this term right here. Di, this term right here, di tilde d epsilon. And I want to set this term del I equal to 0, because if I do so, then I tilde approaches I. And if I'm able to find that, then I'm able to find the function y that minimizes I. So that's what I'm after. And so this is called the first variation of I. Very, very neat. I'm very excited about this class. This is so exciting because to me, it's incredible that we can find this function y that minimizes a functional. That is a very, very cool idea. So how do we do that? How do we do that? So I already told you earlier that the function I, depends on y of x, and that's the integral from x1 to x2. And that is a function of f, which depends on y of x, y prime of x, x dx. And so what I want to do is trying to figure out how do I find that derivative? That's what I want. First, I have to construct I tilde. That's my first step. Construct I tilde. So I tilde then becomes y plus epsilon eta x. And as a consequence, f now becomes a function of y, which is y plus epsilon eta. And notice, I want to be more precise, just so it's clear, y of x plus epsilon eta x. And then y tilde is y prime, the first derivative of y prime. So if y tilde is y plus epsilon eta, then y tilde prime is y prime x plus epsilon eta prime of x. So hopefully that's clear what I've done there. Okay, so here then I get y prime x plus epsilon eta prime x. And now everything is in terms of y plus epsilon eta. So I substituted anywhere I saw y, I substituted for that. And the second thing is that f now is no longer f because obviously they're different. F tilde is what I'll call it this time, if that's okay with you. And so now the idea now is to take that derivative. How do I get that derivative to work? And so I will do that now. So let's do that. So the first variation of I equals, and I'll find the derivative of I tilde respect to epsilon at epsilon equals 0 times epsilon. So that's integral of x1, x2. And so I'll take the derivative of f tilde. And what it would, I want you to notice this, the derivative that needs to be taken is with respect to epsilon. But but f is a function of this whole thing, So therefore, I need to take the derivative a little differently. So that's, first I have to take the derivative with respect to y tilde, chain rule, then respect to epsilon. That's my only way to do that derivative. Because f depends on y tilde, but y tilde depends on epsilon. So that's the only way I can do that. And then I have to take the derivative of f tilde respect to y tilde prime. So the derivative of y tilde prime respect to epsilon. And that's what I get. And then I will evaluate this whole thing at epsilon equals 0, okay, times epsilon. That's what I'm after. That's what I'm after. And I'm getting there. I'm getting there. I'm getting there. Notice that as epsilon approaches 0, then y tends to y tilde. And as epsilon tends to 0, y prime tends to y tilde. And so that's very neat. And we're making great progress right now in how to find that function that minimizes a functional I. Okay, so let's now evaluate each of these with great care. This derivative right here, that derivative right there is easy to find. The derivative of y tilde respect to epsilon is just eta. You can see that from here. The derivative of y tilde respect to epsilon, this y of x has no eta, epsilon. So the derivative of y tilde respect to epsilon is eta x, clearly eta x. And this right here is eta prime of x. You can see that from this second equation here. Very neat, very neat. The second thing I want you to notice, by the way, I forgot to write this to be equal to 0. So let me make sure that's clear. This is equal to 0. And I want to now evaluate this whole thing when epsilon is 0. So now let's evaluate what happens when epsilon is 0. So what happens to this term and this term when epsilon is evaluated to be equal to 0? What happens here when epsilon is 0? I recover the original function f. Tell me if that's correct or not. Can you see that happening? Doesn't f tilde become f and y tilde becomes y when epsilon is 0? Can you see that happening? I'm going very slow, guys, and I have to go slow, otherwise I'm going to lose you. So the derivative of f respect to y now, because when I plug in epsilon equals 0 in here, right, f tilde becomes f and y tilde becomes y. You can see that here. When I put epsilon equals 0, y tilde becomes y. Okay, and f tilde becomes f tilde becomes f. Okay, I'm trying to clean this up so that you can later look at the notes carefully. And I want to remind everybody that I need to see your notes towards the end. So this time eta x plus, then I continue here, the derivative of f respect to y prime, because y tilde also becomes y when epsilon is 0. And so then I get eta prime of x dx, but I have this epsilon, and this epsilon can be multiplied back into here, like that. And so I get this. Very neat. You have no idea. We've made so much progress in trying to figure this stuff out. And I'm excited about it because now the next step is to notice how this multiplication right here is nothing else. Remember, this is del y. And this right here becomes del y prime. Sorry, sorry about that. Del y prime. Remember, del represents the change in height, okay? Del represents the change in height sorry about that, between here and here. Del y is our epsilon eta x. That's what that is, which is the difference in height between y hat and y. Okay, hopefully that's very clear, and it needs to be extremely clear because things are going to get complicated. This is del y and this is del y prime. So now what I have is this expression. I have the integral x1 x2 derivative of f respect to y del y plus the derivative of f respect to y prime del y prime dx equals 0. And the question is, you're still wondering, how am I going to find that function y that minimizes, it's still not clear to you. How do I find that function y that minimizes I, the functional I? But we're getting there because this is the condition that I need to do. This is the condition I need to solve for in order to find that function y. The problem is, it's not very clear what I need to do here. It's not clear what is the next step after this. That is not clear, and that is what we're going to tackle next. Okay, that's what I need to tackle next. And I need to figure out how to get there, and that might not be clear right now to you. But the most theory thing you're going to be doing in this course, so the first thing you're going to be doing in this course over and over and over is integration by parts. And I will teach you how to integrate by parts. So let me go ahead and show you what I had in the previous page. And let me remind you what we're trying to do. I is a function of y of x, and that's the integral from x1 to x2 of f. And this is a function of y prime, and of x, and this is dx. We want to find y minimizing, so it minimizes I. That is my goal. What function y minimizes I? So in the problem of the distance that the curve that minimizes the distance between 2 points, we know what the answer is. The answer is a straight line. And that's what I'm after. That's what I'm after right now. And I hope that is very, very clear. And to do that, what I found that I needed to do is to find the first version of I, and that I have to evaluate y plus epsilon eta of x, the epsilon set equals to 0 times epsilon and set is equal to 0. This is the condition that will allow us to find y that minimizes or maximizes. It could be either or extremizes I, right? And so let's see how to do that. So after I took the first version of I end up with this expression right here, this expression right there. So please take a note of that because I'll be using this expression. So right here, that expression will be used. And so now I'll get started trying to determine how to get there. So I found that the first version of I was this. I did it earlier, but I'll write it down again so it's clear. Partial of f respect to y del y plus partial of f respect to y prime del y prime dx equals 0. We found that this condition right here leads you to this condition right here, and I am stuck. I don't know what is the next step, but guess what? Integration by parts will save your life over and over and over in this course, and I will teach you how to do that effectively. I don't want you to memorize. I don't want you to memorize this at all. This is not something to be memorized, and you're not allowed to memorize it. You're not allowed to use any solutions that are very well known. You have to figure out step by step. And so this right here, what you're gonna do is to write, this is my strategy. My strategy is to remove this prime. I don't want this prime there. If I can remove that prime, that would be very nice. So let's do that. I'm gonna first write this portion right here first on the left side. And then I'm gonna take this portion next here and write it here. And now what I'm gonna do, I'm gonna remove that prime. And the way I'm gonna do that, I'm gonna remove the prime by transferring that prime over like this. Just like I did Gauss term. You're gonna draw a plus and a minus. The cross term that you see, represents the boundary term. So this cross term right here represents the boundary term. This term right here goes inside the integral, back into the integral, okay? So something very important to keep in mind. And so how do I go about that? So let's continue here with the derivation. Del of I equals integral of x1 and x2. I still have this term that I can just write down. Derivative of f respect to y del y. And what I want you to notice is that this is a term, this term right here goes back into the integral. So that's how you integrate by parts, and I'm teaching you how to do that, which is the way I do it, but you can do it many different ways. I believe my way has no memorization, but doesn't mean that that's the only way to do it. And now I have the boundary term, this boundary term here. When you integrate by parts, what you're really doing is you're trying to relate what's inside the body to what's on the boundaries. And so integration by parts lets you do that. And this term that's in the cross term goes in the boundary, okay? And I'm gonna use a different color so it's clear which one I'm doing. I'm doing this term right here. Oh, right here, this is the term I'm doing in the boundary term. And so that's plus derivative of f respect to del derivative of y prime times del y, but now this is evaluated only on the boundaries, x1 and x2. Now, a curve, what is it? What is the boundary of a curve? The endpoints, right? The endpoints are the boundaries of a curve. So that's why there's no normal end shown here. When you go to 2D and 3D problems, this boundary term right here is going to have an end because the end describes the boundary of the surface, the normal to the surface. So it's very important to keep that in mind, and it is important that you don't get confused. Now this is equal to 0, and the good news is that now I can look at, there's two different dimensions of this. There's this integral term, and then there's this boundary term. So they have to independently be equal to 0. Let's first tackle this term right here. That term right there, the good news is, and if you allow me to do this, I'm going to do this next step against your permission, but del y here and del y here show up twice. So I can factor that out for simplicity. I'll just do it right here, del y. It factors out. Why not just do it in one step? And I will ask you this question. If this has to be equal to 0, what are my choices for that to be equal to 0? What are my choices for this to be equal to 0? So let me cover one more time how to integrate by parts. What I did, I took this first term here, 1, and put it here. The second term, which the derivative, I'm trying to remove this derivative here. That's term number 2. The one you're going to remove the derivative goes on the right-hand side under number 2. So you're creating 2 columns. In the first column, you write the remaining term, and the second term is going to have the derivative that you're trying to get rid of. Then you go from here to here by removing that derivative. You can see I removed it. On the left side, what I did, I increased the derivative. You can see that there. Then you're going to draw a plus sign, an arrow with a plus, and an arrow with a minus at the bottom. The term at the bottom here, this term right here, this times that goes back into the integral. So that was this term right there. You can see it, and there's no y prime. So this was just me showing you arrows. And so, and the cross term goes into the boundary. So this times that, and you can see that term right here. So hopefully that's clear. To make that equal to 0, I have only 2 choices. Either del y is 0 or this is 0. But del y should not be 0 inside the boundary, because inside the boundary, I need to have some del y for me able to arbitrary vary y like I did before. And so this has to be equal to 0. And this is by the fundamental lemma of calculus of variations. You have to invoke that every time. Every time you have to invoke that. By the fundamental of calculus of variations, which states that if I have this situation, x1, x2, and I have 2 functions, phi x, gamma x, dx, and this is equal to 0, and gamma and phi is a continuous function. Phi is a continuous function of x, and gamma is an arbitrary function. Then the fundamental lemma of calculus variation says that phi of x has to be 0. That's what it states within the bounds of x1 and x2, not including the boundaries. So therefore, I have no choice to set this equal to 0. That's my only choice. And this is true between x1 and x2, between x1 and x2. So that's what the fundamental lemma of calculus variations tell me, that needs to be the case. And I call this equation is called the Euler-Lagrange equation. It has a name. It's called the Euler-Lagrange equation. If I solve for y in this equation, from this equation, that y is the one that actually minimizes I. So I need to solve that, okay? The second thing I want you to notice is something very interesting. Can somebody tell me what happens to this term? What is going on with that term? I have 2 choices to make that equal to 0. What are my 2 choices? My first choice is that this be equal to 0. My second choice is that this be equal to 0. So I have 2 choices. Either derivative of f with respect to y prime is 0, or del y is 0. Okay, I have two choices. Now, for the very specific problem that I covered today, for the very specific one where I actually didn't specify these endpoints. I did, right? I specified these endpoints. But what is del y at these endpoints? Del y is 0 at those endpoints. So if y is specified at the endpoints, then del y is automatically 0. The other option is I never specify anything on this endpoint. I never specify anything at this endpoint, say. So at that particular endpoint, your other option is that this be equal to 0. That's your other option. I'm going to call this the natural boundary condition. And this here implies that y is specified at the endpoints. And I call this the essential boundary condition. So there's two possible boundary conditions for this term right here. For this term right here, the boundary term. Okay. Your only option is that this be equal to 0 or this be equal to 0. And so now you have the governing equation, you have the boundary conditions, and now you can then go ahead and start moving forward. So now let's go to the problem of minimizing that length. Like, what is the curve y that minimizes that length? And so you're not allowed to use this equation, never. You're not allowed to use this. You have to start from first principles. I showed you already that the length L is given for that particular problem of a function y as a function of x. I already showed you that what I want to do is minimize this curve, the distance, and so that is going to be a straight line. We already covered that. And so, but you don't know the answer, right? No one here knows the answer, right? We are aliens from another planet. We don't know what the answer is. But if I were to teach an alien how to do that, we can probably get there. And I'm going to use some math to do that. And I already showed you that the line, this L, which is this curve right here, we can find that distance by doing this calculation. Y prime squared dx. And so to do that, I have to take what? I have to do what? I have to find the first version of L and set that equal to 0. And that can be done by simply finding the derivative of L, right? Respect to, now I switch and I put this fake. I'm going to put a family of functions of y, examine that one, the derivative with respect to epsilon, set that equal to 0, times epsilon and set that equal to 0. That's the way I want to do it. I can find that derivative very quickly. So this is L tilde now, right? No, there's not L tilde. This is L tilde. And L tilde for our situation is, so what is L tilde? I can do that fairly quick. So L tilde equals integral x1, x2, square root of 1 plus y plus epsilon eta, and that's prime squared dx. Okay, so hopefully that's clear. And so now I have to find the derivative of L tilde respect to epsilon, and that's easily done. So let's do that. Derivative of L tilde respect to epsilon. So another way to write this is to the 1/2. So I have 1/2, 1 plus y prime plus epsilon eta prime squared to the minus 1/2, right? Times the chain rule. So now I have to take the derivative of this with respect to epsilon, and when I do that, I get, am I doing this correct? I have to take the derivative of what's inside, still, chain rule again. So twice 1 plus y prime. So what is the derivative of this with respect to epsilon? That's y prime plus epsilon eta prime, okay, to the 1 power, times the derivative of this with respect to epsilon, because it's, again, it's chain rule differentiation. So I get eta prime. And then I have to evaluate this at epsilon equal to 0 and times epsilon equals 0. So I can now set epsilon equal to 0. So this goes away, this goes away. And so I'm left with integral of x1 to x2. The half goes away. And this is to the 1 power, not meant to be a derivative. So I'll just remove that 1. So you don't think it's a derivative. But you get y prime over 1 plus 1 plus y prime squared. Okay. And you get here, what else you get? You get eta prime times epsilon. And there's a dx missing here. I apologize. So here dx equals 0. And this is nothing more than just del y prime. And so now I'm ready to integrate by parts. This term number 1, term number 2. Okay. And so for term number 1, I'll then write the 4 terms together. And now I have the derivative of this. Plus, minus, and this term right here goes back into the integral, while this becomes a boundary term. Okay, so, sorry, that does not become the boundary term, but the cross term becomes a boundary term. And since the n, so then I get what? I get integral x1, x2 minus y prime 1 plus y prime squared, and all that prime del y dx plus the boundary term plus y prime square root of 1 plus y prime squared del y x1 x2 equals 0. But this term is 0 because y has been specified as boundaries, and at those boundaries del x1, sorry, del, there's no change in height between the virtual solution and the real solution, so del y of x1 is 0 and del y at x2 is 0. So that's why this term goes away. And I'm left with this right here. So then I have integral of x1, x2. I've already integrated by parts, so beautifully done. So I get this dx times y prime 1 plus y prime squared dx, sorry, not dx yet, but del y equals dx equals 0. And then I can invoke by the fundamental, and you have to invoke it like that every time you work on it, by the fundamental lemma of calculus of variations. I can now conclude that for any del y, then what's in parentheses must be equal to 0. And I can solve that very quickly. I can solve this very quickly. I can integrate this by once, just do it once. And I invite you to go ahead and pause the video and do it yourself. I won't go through every step, but you can integrate this by once and then you get y prime. And this is a constant. If I integrate it once, I can square this. So let's call that constant c again, because it's a square. I can now solve for y prime, right? So I can solve for y prime. And when I solve for y prime, it will be a square again. And it's going to look like this, c squared, 1 minus c squared. But guess what? This is a constant again. Call it k. So y prime is now the square root of k. Well, guess what? That's another constant again. But y prime equals a constant. Call it m. Integrate y prime. And so you get y equals mx plus another constant. Isn't that a straight line? Isn't that cool? We found a function y that minimizes the distance between these 2 points. A straight line. We've proven that a straight line is a function that minimizes that curve. Now, that is an incredible finding. And we can also take this further and I can now determine whether this function results in a minimum or a maximum. I can determine that. And the way to do that now, the way I want to do that is examining this term that I didn't talk about today. I didn't talk about this term. But I can go ahead and examine that term. I apologize. I can look at the second variation of I, which is the second derivative of I tilde, like that. And I can, now obviously, then I can check whether it's positive or less than 0. And clearly epsilon squared is greater than 0, so nothing there. But you can then evaluate this as well. And when you evaluate that, you'll be able to determine and show that this in fact will result in a minimum. And it's not very hard to show. You have to just calculate, that derivative, which is going to be a little bit of work. I agree, but it's doable. For example, I want to find the second derivative of epsilon like this, integral of x1, x2 of my original function y, like this, squared, like that, dx, then set is this to epsilon equals 0 times epsilon squared, and you'll find, I guarantee you, that you will be able to determine whether it's greater or less than 0. And that's going to help you determine whether the function is a minimum. You're going to find that it is greater than 0 when you do it, guaranteed. We could do it now, but I don't want to do it because I think it'll be great exercise for you at home when you go ahead and pause the video. So with that said, I have concluded today's lecture. I hope you enjoyed it like I did, because it's my favorite lecture in the whole quarter. And why is my favorite lecture in the whole quarter? Is because I am doing something quite insane, which is given a functional, what function minimizes that functional? And I don't know what that function is. And guess what? I'm able to do that. In summary, what I'm able to do is to take a problem like this. Imagine if this chain hangs like this somehow. I don't know. Obviously, that's not the solution. Obviously, it hangs like the chain that's shown. But using calculus of variations, I can tell you exactly how things look like. I can tell you that the film bubble is going to have that shape. I can tell you that. Okay? I can tell you that. I can tell you a lot of things. I can tell you how the airplane deforms using calculus variations, and that's why we're trying to study this, is to bring some sense to finite elements, to give you a sense of how we can solve very complicated problems moving forward.